This is Ham College, episode 106, for October 27, 2023. Ham College is brought to you by Icom. Keep your competitive contesting edge with Icom. Icom's high-power base stations cut through pileups, letting you work the bands and record those contacts. Heard it, worked it, logged it. Good evening. Welcome to another episode of Ham College. I am Professor Thomas.
And I'm Dean Martin.
And we've got more amateur extra exam questions for you tonight. It's, part 44 of the questions.
Wow.
There's been a lot of questions.
A lot of parts.
Yep. And a few more to go. What did we talk about last month?
Well, let me see. Let me reach way back in the memory banks. I believe we talked about antenna parameters, radiation resistance, gain, beam width, efficiency, effective radiated power, maybe. Best I can recall.
That works pretty good for you.
It does. I just kind of got to get it started.
It's just not focusing quite as good on the paper, though, is it? This month we're going to talk about antenna patterns and designs, E&H plane patterns, gain as a function of pattern, and antenna modeling.
Oh, boy.
Some more antenna stuff.
And more buzzers.
Nah, maybe not.
I know there's some charts on this one, and I'm not quite sure how to read those charts, so we'll see.
We'll figure them out. After the first one, I bet, and I don't know who it's going to land on, but after the first one, you'll be able to figure them all out, I think.
Okay. In the antenna radiation pattern shown in figure E9-1, what is the beam width? A, 75 degrees.
B, 50 degrees.
C, 25 degrees.
Or D, 30 degrees. So the way you read this chart, on the right-hand side, 0 degrees. Right opposite of that, 180 degrees. So it's just 360 degrees all the way around, I would say. But those numbers aren't adding up, are they? They are, because you count from 0. If you go counterclockwise, you're going 30 degrees counterclockwise, 60, 120, 150, 180. If you're going clockwise, minus 30, 60, 120, 150. Depends on which way you go. The farthest you can get is either plus or minus 180 degrees. You know, that's interesting. Plus or minus 180 degrees is the same thing. So that's going clockwise and counterclockwise. All right, you see there's different sizes of rings there in that chart. The outer ring would be 0 dB, because you can see on our antenna pattern, the very tip of it hits right at 0 dB. It's the referencing against the actual main lobe of the antenna here. It's easier if you look at the top. The outer circle is 0 dB. The next circle down would be minus 3 dB less. The next one down would be minus 6. Next one down, minus 12. Then minus 24. And they don't have the next one marked, but it's probably minus 48. And what we're trying to do is determine the beam width. And the beam width we count out to minus 3 dB. All right, if you look at the minus 3 dB ring, which is the second ring in, looking on the right-hand side there.
Okay.
You see right at 0 in the center, we go about 25 degrees above 0, and minus 25 degrees is where the pattern crosses the minus 3 dB range there.
The question doesn't say anything about 3 dB.
No, it doesn't. But so you have to know that when you're measuring beam width, you're thinking about minus 3 dB over whatever it is.
Okay, so if it's not stated, that's what you're going to look at.
That's what you're going to say. Now, if they gave you some other, spec, but 3 dB is typically what you're looking at. So we can see our pattern is crossing the minus 3 dB at 25 degrees either side of 0. So altogether, that's 50 degrees. So I'm going to say answer B. Makes sense?
Mostly.
Yeah,
I think so.
Okay. All right, I got a question for you then, since you know how this works now. In the antenna radiation pattern shown in figure E9-1, what is the front to back ratio? Is it A, 36 dB,
B, 18 dB,
C, 24 dB,
or D, 14 dB? Front to back ratio. I'm going to say that looks like it might be 18.
How are you coming up with that?
What's the lobe in the rear at 180 degrees is falling between 12 and 24. It's
Yeah.
probably around 18.
I'm going to agree with you. There you go.
Okay.
Okay, you got this.
You got that one.
Yep, right at the rear of it, that is about 18 dB.
Yeah.
We can see minus 12 where it is. 24 is the next circle in. That's crossing about, that's closer. It's a close call there. Is it 14 or 18, but it's closer to 18.
In the antenna radiation pattern shown in figure E9-1, what is the front to side ratio? A, 12 dB,
B, 14 dB,
C, 18 dB,
or D, 24 dB. So I'm looking at those two side lobes, which are going to be the ones that are straight up and down.
12,
Actually,
14, 18,
yeah, I'm looking at this
24.
one and this one. So front to side, well, the front is 0 dB, so I'll start coming up. That'd be minus 24 dB there. That's 12. I'm going to say, what are my choices there
12,
again?
14, 18, or 24.
I'm going to say 14. It looks to me like it's closer to being 14 than it is to being
Yeah,
18.
I would concur with that, Professor.
And it's the same thing on the bottom. It's the same on both sides of the pattern there. So I'm going to say it's answer B. The chat room, yeah, they all got this one. Whatever that means.
Whatever. I
Yeah.
don't really want to know.
So here's explaining right
And that
there.
pretty much says it all.
Yep. We got the minus 12 dB circle there. We're a little bit inside of it, about minus 14. That's all you can say about that.
That's enough. It's plenty.
What is the front to back ratio of the radiation pattern shown in figure 9-2? A, 15 dB,
B, 28 dB,
C, 3 dB,
and D, 38 dB.
So what is the front to back ratio of the radiation pattern? Front to back ratio.
Okay, so I'm going to say that that's probably, what are the choices again?
Your choices are going to be 15, 28, 3, or 38.
I'm going to say that probably looks like around 28.
Yeah, I would say it's just a little over the minus 30, which would, yeah,
Roughly 28.
that's answer
Eesh.
B.
28. I got
28.
it.
So it's B.
Go
Okay.
figure. I just thought I didn't know how to read the charts.
That's what you were telling me. I knew you had this, though. It's when we turn over these pages here to the next side, those are the ones that I'm not sure if we got.
Yeah?
We'll have to wait till we get there. But we got some more like
I
these.
don't even know what those questions are, honestly. I haven't even looked at them.
Top red there, minus 30. Well, that arrow's pointing to minus 30 line there. And then down below that, minus 20 is the next line out. And so your back ratio, the back part of the pattern there, is right at, well, it's between 20 and 30, but it's almost right at minus 30. So it's just a little bit more than that, minus 28.
What type of antenna pattern is shown in figure E9-2? A, elevation.
B, azimuth.
C, radiation resistance.
Or D, polarization. So let's see, elevation, azimuth, radiation resistance, or polarization. All right, it's not polarization. I can say that. It's not radiation resistance. I don't see any ohms on there. So that leaves elevation or azimuth. And being the way that it's looking, like at the bottom, it's 0. And as we're going up, I'm going to say it's elevation.
Yeah, I mean, it makes sense judging by the markings on the
Yep.
chart as well. It says over real ground as well.
Mm-hmm.
90 degrees would be straight up in the air.
And what are the people in the chat room saying? They're all saying A, which is elevation.
Yeah.
Next question. What is the elevation angle of peak response in the antenna radiation pattern shown in figure 9-2? Is it A, 45 degrees?
B, 75 degrees?
C, 7.5 degrees?
Or D, 25 degrees?
What is the elevation angle of the peak response?
What was the answer choice? 7.5?
7.5, 25, 75, or 45.
I'm going to say 7.5 because each one of those are 15 degrees segments. And the main lobe is about middle ways, so that should be around 7.5.
Yeah, I'm going to agree with you. You're talking about right about there.
Yes.
And that is 15. Chat room, pretty much saying the same thing.
That's my final answer. Me and this guy. He's been helping me cheat.
Yeah. Y'all got it.
We nailed it. Way to go. Way to go, Scully.
I hadn't named him, but that's a good name for him.
Yeah.
Yeah. Well, that's the first half of the questions.
All right.
So if you were worried about numbers, you got through all of them. What do you say we take a quick break?
More coffee, Tom?
No, thanks, dear.
Try one of these Geno's pizza rolls, Brad. They're great.
Okay. It's a nice party, Mrs. Clark.
I see your husband didn't like your coffee.
I beg your pardon.
I'm Mrs. Johnson. You should try my coffee.
Look, I don't know who you are or how you got into my house, but you take your coffee and leave, okay?
Igor, go and get me what I crave. Evening, Igor.
If you want a better orange soda, made with more natural orange flavor than ever before, try Shasta. It's got the bright color, the sweet smell, and the great taste of oranges. Shasta. It's the orange soda that can make anybody happy.
Keep your competitive contesting edge with Icom. Icom's high-power base stations cut through pileups, letting you work the bands and record those contacts. Contest from the comfort of your home or remotely with the RSBA1 app. Heard it, worked it, logged it. The IC7851 gives you a new window into the RF world and is HF excellence unparalleled. With faster processors, higher input gain, higher display resolution, and a cleaner signal, it's truly the pinnacle of HF perfection. Dual receivers, digital IF filters, memory keyer, digital voice recorder, high-resolution Spectrum waterfall display, enhanced PC connectivity, and SD memory card slot. The IC7610 is the SDR every ham wants. This high-performance SDR can pick out faint signals in the presence of stronger adjacent signals. The Icom IC7610 is a direct sampling, software-defined radio that has changed the world's definition of an SDR. RF direct sampling system, 110 dB RMDR, independent dual receivers, and dual digicell. Icom's IC7300 is a high-performance, innovative HF transceiver with a compact design that will far exceed your expectations. This innovative HF transceiver digitizes RF before various receiver stages, reducing the generated inherent noise in different IF stages. This is a radio that changed the way entry-level HF is designed. RF direct sampling, 15 discrete bandpass filters, large 4.3-inch color touchscreen, real-time spectrum scope, and SD memory card slot. The real HF fun starts here. For more information about Icom's amateur offerings, visit icomamerica.com/lineup/amateur.
What do you say we give away something?
Well, what we got here? We can't give away Scully. We got these cool t-shirts. I bet you somebody'd like to have one of these. I got one like it. I love mine. Nice ham crew t-shirt. Compliments of Icom.
You look just as good coming as you do going trick-or-treating.
Or wherever you want to go.
Yep.
Yep.
If you'd like to win one of those, well, it's pretty simple.
What do you got to do?
Well, why don't you tell them while I
can do that.
find us a winner here.
You don't have to be a licensed ham or anything. All you need is a name and an email address. Send us an email, hamcollege at AmateurLogic.TV. And you don't need to put a note or anything. If you'd like to put one in, that's fine. We like to read them, but otherwise you don't really have to. That's all you got to do to enter. George is about to draw the winner for this shirt. And then the list will be cleared out, and then you can start over again. If the list gets cleared, names don't carry over if you didn't win. So if you entered this month, you didn't get called, be sure to enter again for next month. Oop, we got a winner.
He had a message in here. He said, sent from my iPhone.
Oh.
And it is from, I'm not sure how you pronounce his last name, Sal. I can get his first name right.
Your call sign?
There's not a call sign. Sal Genusa, Genusa. Does that sound good to you?
Sounds perfect to me.
All right. Congratulations, Sal. Icom will be in touch and be sending you.
It's a good-looking shirt and whatever else they put in the box.
Yep.
Good chance there'll probably be some other goodies in there.
It always is.
How does the total amount of radiation emitted by a directional gain antenna compared with the total amount of radiation emitted by a theoretical isotropic antenna, assuming each is driven by the same amount of power? A, the total amount of radiation from the directional antenna is increased by the gain of the antenna.
B, the total amount of radiation from the directional antenna is stronger by its front-to-back ratio.
C, they're the same.
D, the radiation from the isotropic radiator is 2.5 dB stronger than that from the directional antenna. How does the total amount of radiation emitted by a directional gain antenna compare with the total amount of radiation emitted from a theoretical isotropic antenna, assuming each is driven by the same amount of power? I know the answer to this one. And rather than read all those wrong answers, since they are kind of wordy.
The total amount of radiation emitted by a directional gain
Yep.
antenna compare with the amount of radiation
Here's
emitted by
here's the clue. A directional antenna, all it does is takes the power you put in and direct it wherever you want it to go, or hopefully where you want it to go.
Concentrates it.
Yeah, it concentrates it. It takes away some from over here and puts it over here.
Mm-hmm.
So there's no more power coming out of that antenna. It's just all put in the direction you want it, or more of it's put in the direction you want it. So, yeah, what you put in is what you get out. So I'm going to say C. They're both the same. It's just it's going the way you want it to. But there's no more power because you just took it from one direction, put it in another.
Antenna is a total amount of radiation. Okay. Yep.
They're all saying C over in the chat room. Make sense to you? You're looking like it doesn't.
Well, it does, but I was thinking about like ERP and the gain of the antenna. I guess it's still the same amount of watts.
Yeah. I mean,
But it acts like more watts. If you got 3 dB of gain, it acts like double.
yeah, in that direction.
Yeah.
Over here, it acts like 3 dB less because you took away 3 dB here and you put it over
Right.
there. So, or roughly. So, yeah. The gain of an antenna is, it really doesn't increase the signal overall, but just in the directions that it does. It just optimizes it in certain directions.
Okay. How about that?
Here we go.
It's kind of a little bit of a trick question.
Yeah, well, they're throwing away or putting in more information than you really need.
It'd be pretty easy to get mixed up and consider that A. But I see what you're saying.
Yeah. What is the far field of an antenna? A, the region of the ionosphere where radiated power is not refracted.
B, the region where the radiated power dissipates over a specified time period.
C, the region where radiated field strengths are constant.
Or D, the region where the shape of the antenna pattern is independent of distance. I'm going to guess it's D, I think, but I'm not 100% sure, but that seems like the answer.
Yeah, I'll agree with you.
D, okay.
Yep, there you go. I think a little explaining is in order.
It wouldn't hurt.
The near field refers to places nearby the antenna conductors or inside any polarizable media surrounding it, where the generation and emission of electromagnetic waves can be interfered with while the field lines remain electrically attached to the antenna. Absorption of radiation in the near field by adjacent conducting objects affects the loading of the signal generator, the transmitter. The electric and magnetic fields can exist independently of each other in the near field, and one type of field can be disproportionately larger than the other in different subregions. An easy-to-observe example of near-field effect is the change of noise level picked up by a set of rabbit ear antennas when a human body is moved in close to the ears. Now, this picture that I'm showing here really is not demonstrating near field and far field, but we can use it for that. So that's what near field is. Anything close in can affect the pattern. But as you get out farther, it doesn't. So the far field is a region in which the field is settled into normal electromagnetic radiation. In this region, it's dominated by transverse electric or magnetic fields with electric dipole characteristics. In the far field of an antenna, radiated power decreases as the square of distance, and absorption of the radiation does not feed back to the transmitter. In the far field, each of the electric and magnetic parts of the EM field is produced by or associated with a change in the other part. And the ratio of electric and magnetic field intensities is simply the wave impedance in the medium. So that's a lot of fancy talk there on some of that. But basically...
Yeah, basically it means the basic design of the field strength of the antenna, that it's the pattern of the antenna.
So what it's talking about is when you're in close to the antenna, like if we were in real close here, some of these lobes are overlapping with each other very close in, and there could be other objects in here, other pieces of metal. On the case of higher frequencies, VHF, UHF, somebody standing there could make a difference. But when you're near in, that pattern's going to change as you move out. These lobes aren't going to be overlapping with each other. they're going to become stabilized out here, and you can go farther away, and the ratio stays the same, say between this lobe and this one, and the null in between it stays the same ratios too as you're on out. When you're in closer though, you see they're not. I mean, they're overlapping. Things are getting reflected back to the antenna as well. Mm-hmm. So in the near field, you got more distortion of the antenna pattern.
That makes sense.
Well, I'm sticking with that. Tom says, in the region where near field becomes far field, variably specified somewhere between 1/2 and 1 wavelength, it's named the Fresnel zone. Yes. The same guy that invented the Fresnel lens in lighthouses. And one place I read that the far field really starts several wavelengths out. But another place I did read, it was a little under a wavelength that it started. But I think that's going to vary from situation to situation, depending on what else is close to you. He hadn't said a word all night.
He's just taking it in.
Yeah. Well, good. Maybe he'll pass. All right. Let's see. You answered that one?
Yes, I did. We haven't had a buzzer tonight. That's unusual.
We haven't.
'Cause I thought when I saw what the things were, I thought there'd be quite a few of them, to be honest with you. What type of computer program technique is commonly used for modeling antennas? A, graphical analysis.
B, method of moments.
C, mutual impedance analysis.
D, calculus differentiation with respect to physical properties.
That's a mouthful.
What type of computer program technique is commonly used for modeling antennas? Not graphical analysis. It's not mutual impedance analysis. Calculus differentiation with respect to physical properties. I'm not sure exactly what that means, but I do know that it's method of moments is what is used by the FCC on a lot of stuff.
Really?
Yeah. So I'm going to go with that. I'm going to say B, method of moments. Chat room, the ones who are answering are saying B.
Some of them are kind of tough when they don't answer a lot out there. You know that they're a little tougher than...
Yeah. There's your sign. What is the principle of method of moments analysis? A wire is modeled as a series of segments, each having a uniform value of current.
B, a wire is modeled as a single sine wave current generator.
C, a wire is modeled as a single sine wave voltage source.
Or D, a wire is modeled as a series of segments, each having a distinct value of voltage across it. I'm going to guess D.
That was a buzz.
I was wrong. It's A.
A wire is modeled as a series of segments, each having a uniform value of current.
I almost changed to that, but I didn't, obviously. So that's a buzzer.
I told you I'd heard of method of moments, but I really didn't know what it was, other than the FCC liked it.
Yeah.
I did a little study here.
Okay.
And here's what I come up with.
Give us some learning, Professor.
The method of moments, also known as moment method and methods of weighted residuals, is a numerical method in computational electromagnetics. It's used in computer programs to simulate the interaction of electromagnetic fields. Antenna simulation programs like NEC calculate the radiation pattern of an antenna. Generally being a frequency domain method, it involves the projection of an integral equation into a system of linear equations by the applications of appropriate boundary conditions. And right here is where I fell asleep.
Yeah, I can see that.
This is done by using discrete meshes and is finite differences and finite element methods, often for the surface. The solutions are represented with the linear combination of predefined basis functions. Generally, the coefficients of these basis functions are the salt unknowns.
Salt unknowns?
Salt.
Salt.
S-O-U-G-H-T. And I was going to read that earlier, but I didn't. So I have a part 2, which is what I was really supposed to read right now. In the method of moments, the antenna wires are modeled as a series of segments, and a uniform value of current in each segment is computed, which was basically the answer there. The field resulting from the RF current in each segment is evaluated along with the effects from other mutually coupled segments. The higher the number of segments, the more accurate the modeling. Many programs have a limit on the number of segments in a particular antenna because of the amount of memory and processing power that is required to perform the calculations. A lower number of segments reduces the time needed for modeling calculations. However, outputs like antenna pattern studies and feed port impedances are not as accurate. Well, that makes sense. If you're not using as much data to come up with the answer, it's probably not going to be as accurate. So, method of moments. We got one more question tonight, and you can ask me this one.
It's pretty interesting stuff, man. How they could do that. I'm going to look into that. That's kind of fascinating to me.
Is it?
Yeah. I might take a play around with that.
Well, a lot of people do. They use a mini neck or easy neck or one of those necks. The real
neck.
Yeah, the real neck costs real money, but there are free ones out there.
I like how the easy one sounds.
Yep.
Easy's good.
You can report back on if it was.
Okay. I'm thinking it probably won't be, but we'll see. Okay, here's the question for you. The final one of the evening, you say, huh?
Yep.
What is a disadvantage of decreasing the number of wire segments in an antenna model below 10 segments per half wavelength? A, ground conductivity will not be accurately modeled.
B, the resulting design will favor radiation of harmonic energy.
C, the computed feed point impedance may not be correct.
Or D, the antenna will become mechanically unstable. What's the disadvantage of decreasing the number of wire segments in an antenna model below 10 segments per half wavelength? I don't think when you're doing antenna modeling, you're really modeling the mechanic stability of it. So yeah. I'm going to knock D out. I don't think it's got anything to do with antenna modeling.
Okay, I'll buy that.
A, ground conductivity will not be as accurate. Ground conductivity is going to be whatever ground conductivity is, no matter how you're modeling your antenna. That's not going to change the ground conductivity in your area. B, the resulting design will favor radiation of harmonic energy. I don't think so. C, the computed feed point impedance may be incorrect, and I'm going to go with that because if you're decreasing the number of wire segments, that means you're reducing that amount of data you're working with. And when you're modeling antennas, that is one of the things that you get out of it is a computed feed point impedance. So I'm going to go with that. I'm going to say...
kind of makes sense.
Yeah, I'm going to say C. Chat room?
C,
yeah,
the ones that answered.
Yeah.
Not too many answers in there.
There we go.
Nailed it. Here, I'll give you that.
All right, I've been needing that, man. This is a tough bit of explaining to do here tonight.
Yeah.
Tough bit of answering to do too, wasn't it?
Yeah, it's a little bit.
Yeah.
I thought it was going to be worse, though, honestly.
Yeah. If you learn one of those charts there,
Yeah, that kind of
you
makes
can-
sense.
Yeah, you can get them all from there. So that's it. That's all the questions we have tonight.
What do you think about it, Scully? He's waiting for more. He's just sitting there staring at the screen waiting for the next ones to come
Well,
up.
Scully will be back next year, hopefully. My wife had packed him away in a box.
Oh, yeah?
Yeah. And he came out for the holidays.
Yeah. It's
So
good to let him out every now and again.
I
He's been pretty well behaved.
bought a couple of big bags of candy. And I'm hoping we're still going to have some when Halloween gets here next week. They've gone down a little bit.
Yeah. I got ours and I tied it up and it's like, don't touch this until
Yeah.
Halloween night. So
I should have hid mine somewhere.
you've only been getting into it?
I'm one of the ones.
Yeah.
Anyway, he got all the answers right by the skin of his teeth. That's pretty accurate there, Tom. Any final thoughts? Like Scully here?
No, don't
No.
don't raid the Halloween candy before it's time so you don't have sugar confusion.
Yep. That's a good idea there. I'll say happy Halloween.
Yeah, happy Halloween and yeah, we'll see you in a few weeks.
That works.
Few, 2, 3,
Yeah.
whatever, in some weeks.
We'll see you in November
Yep.
or December 1st. Sometime in there.
Yep. You count on that. We'll be back.
7-3.
7-3.
You know, that's an odd looking pattern.
It is. What kind of antenna is that?
That's a good question. It's a Chick-fil-A.
Yeah, it looks like the one your kids used to make in kindergarten when you put their hands on the construction paper and traced their fingers.
No, that was that kid that was missing the little finger.